in this video, I wanted to talk about some very important trends that we can actually track on the periodic table. So the periodic table can be used to track these important physical and chemical trends. And one of the important ones is the number of valence electrons. So these are the electrons in the outermost energy level, and these are very important for bonding. And these valence electrons follow a predictable trend on the periodic table. There are other periodic properties that we can look at, and these are just properties of the elements that have regular changes that can be tracked on the periodic table. And these include things like the atomic radius, which is just literally the size of the atom, the ionization energy. This is how easy it is to remove an electron from an atom. There is electron affinity, which is just kind of the opposite of that. It's how easy it is to add an electron to an atom. And then there is electronegativity, which is how strongly atoms pull electrons from other atoms. And this is actually talking about atoms in the context of molecules, and so we'll talk more about this in future videos. We won't cover it as strongly in this one, but it's essentially how strongly atoms within a molecule pull electrons away from other atoms within a molecule. And then metallic character, we'll talk more about what that means later in the video, but it's just essentially how much something behaves like a metal. So the valence electrons we can actually track, like I said, across the periodic table. So if we look at these two atoms here, they're both in the same row, but they're in different columns. We can look at the differences in their outermost electron energy levels. And so if we look at our Bohr models here, we see that nitrogen has 7 protons and 2 shells of electrons, and oxygen 8 protons and 2 shells. So they both have the same number of electron shells, but the oxygen has 1 more proton than the nitrogen. So if we look at just the outer shell of nitrogen, we see that we have 1, 2, 3, 4, 5 electrons, and so that means that it has 5 valence electrons. Then with oxygen, if we look at its outermost shell, we see it has 1, 2, 3, 4, 5, 6 valence electrons. So 6 electrons in the outermost shell means that it has 6 valence electrons. And if we look at these two atoms here, so these are both in the same row as each other, but they're in the next row down from the ones we just looked at. But they're in the same 2 columns as the ones we just looked at. So phosphorus, if we look at its outermost shell, it has 1, 2, 3, 4, 5. So it's in the same column as nitrogen, and it too has 5 valence electrons. Sulfur, it's in the same column as oxygen. If we look at its outermost shell, it has 1, 2, 3, 4, 5, 6 valence electrons, just like the oxygen. And so what that tells us is that things that are in the same column have the same number of valence electrons. So in this first column, everything has 1 valence electron. The second column, everything has 2. The third column, everything has 3, then 4, 5, 6, 7. And in this last column, everything below helium will have 8 valence electrons. Helium can only have up to 2 electrons, and so that one will not have 8 valence electrons. But everything below helium will have 8 valence electrons when it's in that column. And this is not as applicable to these D block elements here because these don't follow valence electron theory as well as the main group elements. And so what we see is that the number of valence electrons that these have is equal to the group number for the main group elements. And we can show this using what are called electron dot symbols or Lewis dot symbols. So with sodium, for instance, this is in the column 1A, and so this has 1 valence electron. So we just put a single dot by it. And with magnesium, it's in 2A, so we have 2 dots by it, and we see that I'm kind of putting these in going in counterclockwise order, and we put 1 to the right, then 1 above, and so we will just kind of keep adding them in that order. So then aluminum will have 3 valence electrons, so it has 1, 2, 3. Then silicon has 4, it'll be 1, 2, 3, 4. Then phosphorus, it has 5, so it'll be 1, 2, 3, 4, 5. And what you'll notice is then I start pairing it up once we get past 4. In a course like this, we don't really go into why that's the case, but this is important for bonding theory that we have these paired electrons and these lone electrons. So this is just something that you have to kind of remember. Then for sulfur, we have 6 valence electrons, so it'll have 1, 2, 3, 4, 5, 6 like that. So again, we're pairing up the ones after 4. Then chlorine, we have 1, 2, 3, 4, 5, 6, 7. Then for argon is 1, 2, 3, 4, 5, 6, 7, 8. And so again, this means that the number of valence electrons for main group elements is just equal to its group number or its column number. And this works for all of these, except for helium, of course. But we see that everything in the 1A is going to have 1 valence electron, 2A is going to have 2, 3A is 3, 4A is 4, 5A is 5, 6A is 6, 7A is 7, 8A is 8, except again for helium, which can only have up to 2 electrons. But for everything else, we see that the column number or the group number is going to be the same number of valence electrons that it has. So we have a few other important periodic trends we want to talk about, and these periodic trends are trends in certain physical and chemical properties that can be tracked on the periodic table, which again is one of the strengths of the periodic table. It allows us to track these properties and predict what sort of properties things might have. So all periodic trends are caused by essentially the same two phenomena. Really, it ends up being kind of one phenomenon, but we can think about it in two different ways. So the first one is just how strongly the negatively charged electrons feel the attractive force of the positive charges from the protons in the nucleus. And the important part about this phenomenon is this has to do with how many protons there are. So for instance, if we have one proton and one electron, where the electron has a charge of -1, the proton is +1, and they're at a distance r, this is what the electrostatic attraction is going to be. So it's going to be this F sub 1 right here, where we see that it's going to depend on the charges multiplied by each other in the numerator, then the square of the distance in the denominator, where this k is just a constant. We won't have to worry about that. And so if we see that we have now 2 protons and 1 electron, so we have -1 for the electron and now +2 for the protons, and they're still at a distance r away from each other, then the electrostatic attraction will be this. So this F sub 2, we now have a 2 in the numerator here, which is going to mean that F sub 2 is greater. And in fact, it's 2 times greater than the F sub 1, and therefore there is more attractive force on the electron in the 2 proton system than there is in the 1 proton system. And so that's why even when you're going across a row on the periodic table, you're going to get increased attractive force on the electrons. And so if we look at that using these 2 atoms right here, nitrogen and oxygen, this is what we have again with our Bohr models. The nitrogen has 7 protons, the oxygen 8 protons, and they both have just 2 electron shells. And so that means that the distance between the nucleus and the electrons is going to be about equal. So this is our force of attraction for nitrogen on the left, and the force of attraction for oxygen on the right here. And so we're saying that these are both in the second shell, so the R for the nitrogen is going to be equal to the R for the oxygen. And so that means because the oxygen has a greater number of protons in the nucleus, that means it's going to have a stronger attractive force on those electrons. And so each electron for the nitrogen in the outer shell feels 7 protons worth of positive charge from a distance of 2 shells away, and in the oxygen, each electron in the outer shell feels 8 protons worth of positive charge from a distance of 2 shells away. And so that means that the force of attraction for oxygen will be greater than the force of attraction for nitrogen. And what this ends up actually doing is meaning that the distance between the nucleus and the electrons and oxygen gets somewhat reduced. And that's because the electrons in that shell feel a stronger attractive force that's going to pull them in slightly closer than it would be for the nitrogen. And so that will actually reduce the size of the oxygen atom relative to the nitrogen atom, which can be somewhat counterintuitive because remember, oxygen is further to the right on the periodic table than nitrogen. And so that will mean, as we'll see here in a little bit, that the size of the atom actually decreases as you go left to right on the periodic table. The second phenomenon here is just how many shells of electrons there are, with higher shells being further away from the nucleus. And so that means they actually feel less of the positive charge. So if we think about our proton and electron system here, where the electron is -1, the proton +1, they're a distance r, and they feel this electrostatic attraction F sub 1. And then if we have something like this where the proton and electron are twice the distance away, so the electron is still -1, the proton +1, and the distance is now 2r, that means that the electrostatic attraction will be this, where we see we have 2 down here in the denominator. That 2 actually has to get squared, so it becomes a 4. And so that means that the F1 is going to be 4 times greater than the F2. Even though we're only doubling the distance, it means that we're going to cut the attractive force down by 75%. It's going to be 1/4 the attractive force. And so that means when we have them closer together, the attractive force is stronger than when they are farther apart. And so again, we can look at a couple atoms here. So these are in the same column, but in 2 different rows. And so these are the Bohr model diagrams for them. So the nitrogen has 7 protons in 2 shells. The phosphorus has 15 protons, but in 3 shells. And so we can look at the distance from the nucleus to the electrons in the outermost shell, and we'll call that lowercase r for nitrogen, uppercase R for phosphorus. And so these are the equations for this. So this is the force of attraction for nitrogen and the force of attraction for phosphorus here. And so what we see is, because again we're squaring these, that the capital R squared here is going to be quite a bit larger than the lowercase r squared here. And so even though phosphorus has more protons in the nucleus, it's going to actually feel less of that attractive force because the electrons in the outermost shell are further away. And so each electron in the outer shell of nitrogen feels 7 protons worth of positive charge, but it's from a distance of 2 shells away. Where for the phosphorus, the 3rd shell is further away from the nucleus and so feels less of that positive charge. Because remember, again, when we have the distance here, we're actually squaring it. So that's going to make a bigger difference than adding those extra protons. And so that means that the force of attraction for nitrogen is actually greater than the force of attraction for phosphorus. And so given these 2 phenomena, we can look at some of the trends in the periodic table. So the atomic size, as I said, as we go left to right, we're actually going to decrease the radius because we're adding more protons, but we're not adding any more shells onto it. So each of the electrons in the outermost shell will feel more of that positive charge, which will pull them closer to the nucleus. Then as we go from top to bottom on here, we're just adding more shells onto it, and so that's just going to increase the size of the atom. So we see that things in the upper right are going to be smaller, things in the lower left are going to be larger. And then ionization energy, which is another important periodic trend. So it's the amount of energy required to remove the outermost electron of an atom, and this is usually measured in the gaseous state. And so when we remove an electron from a neutral atom, a cation with a positive charge is formed. And so again, we see that this will follow in a single column, that as the electron gets closer to the nucleus, it's going to take more energy to actually remove that electron. And again, that's because it's going to feel more of that positive charge. Just like 2 magnets, if you have them closer together, it makes it harder to pull them apart. And so this is our trends for ionization energy, where we see as we go left to right, we increase the ionization energy, it becomes more and more difficult to remove an electron. And again, that's because we are increasing the number of protons without increasing the number of shells as we go left to right. And so that means that it's going to be more and more positive charge that those electrons feel, and so that's going to make it harder to pull those electrons off. Whereas if we are looking in the single column, then we have to use that second phenomenon where, remember, we're adding more shells as we go top to bottom, and so that means that the electrons are further away, they're going to feel less of that positive charge. So as we go top to bottom, it becomes easier to pull electrons off, but as we go bottom to top, it becomes more difficult. And so that's why we have the increasing ionization energy as we go from bottom to top on the periodic table. This is just another way of looking at the ionization energy, where the height of each of these is the ionization energy for it. So again, we see stuff in the upper right here is going to be higher. That means it takes more energy to pull electrons off because of those 2 phenomena we talked about, where stuff in the bottom left is going to be easier to pull the electrons off because of that phenomena we talked about. Then electron affinity, this is essentially the converse of the ionization energy, where we see that it's actually going to be easier and easier to put an electron on as we go to the upper right, and harder to put an electron onto the atom as we go to the bottom left. So the electron affinity is how easily you can add an electron to an atom and turn it into a negatively charged ion. And so stuff over here in the upper right is going to be very easy to add electrons onto them. Stuff in the bottom left is going to be much more difficult to add electrons to those atoms. And then electronegativity is how strongly the atom pulls electrons toward itself. So this actually trends the same as ionization energy and electron affinity. That's because it's essentially just talking about the same thing. So if we're talking about how strongly the atom pulls electrons toward itself, that's essentially just the same thing as electron affinity. But electronegativity, like I said earlier, is talking about this in the context of atoms that are bound together into a molecule. And so we'll talk more about electronegativity in later videos, since it's very important for many physical and chemical properties of compounds. So physical properties such as the boiling point, melting point, and solubility in different solvents, and chemical properties such as reactivity, which is what other things something will react with and how it will react with them. So again, this electronegativity is very important, but this just trends exactly the same as the ionization energy and electron affinity, because they're essentially just the same phenomenon but talked about in sort of different contexts here. And we can look at that with a table that looks like this, where again the height of it is telling us how strongly electronegative something is, where just like with the electron affinity and ionization energy, we see stuff in the upper right is very strongly electronegative, stuff in the bottom left is very weakly electronegative. Then metallic character, so this is the extent to which something exhibits the following properties. So electrical conductivity, this would just be how much voltage is required to get an amount of electric current to flow through something. So metals we know are highly electrically conductive, and so high conductivity just means that it requires lower voltage. So we know that things that are more metallic are going to be more conductive to electricity. Similarly, they're going to be more conductive to heat. So heat conductivity is just the ability of a body to transfer energy in the form of heat in a non-uniformly heated solid. So non-uniformly just means that if you have a piece of metal, you heat one end of it is hot, the other end of it is cold, and so we want to know how easily or how fast the heat will just sort of move through the metal to the other side so that it heats it up uniformly. So how fast it goes from non-uniformly heated to uniformly heated. And so high conductivity just means that it transfers the heat faster. And we know that things that are more metal are going to be more highly heat conductive. That's why we use metal for things like pans, because we want the heat to move through that metal into whatever we're trying to heat up very fast. And that's why we use things that are very unconductive to heat as heating pads, because we want to grab something out of the oven without it moving through our heating pads very fast before we can set it back down. And so then malleability is another of these metallic characters. So this is just the capability of being shaped or extended by hammering or forging. And ductility, which is a very similar property. So it's just the ability of a material to have its shape changed as if being drawn into a wire or thread without losing strength or breaking. So metallic character just includes these properties here. And again, what we see is that as we now go in the opposite direction, so as we go right to left, we get increasing metallic character. As we go top to bottom, we have increasing metallic character. But we can see that this trends in essentially the opposite way as all the other ones we saw, things like electronegativity and ionization energy and electron affinity. And so this ends up being just because of those same two phenomena we talked about. And so something like phosphorus is very non-metallic. So if you look at a pile of phosphorus, you can see that it just doesn't look very metallic. But something like cesium is extremely metallic. It's way over in the bottom left. And so cesium would actually be very metallic. And everything else in between would show sort of intermediate levels of metallic character. And so this just kind of sums up a lot of these things we were talking about, where we see, again, that ionization energy and electron affinity increase as we go left to right and increase as we go bottom to top, where atomic radius is actually going to increase as we go in the opposite direction, and metallic character is going to increase as we go from the top right to the bottom left. And again, these are all just different ways that this same phenomena actually manifest. And so essentially what it means is that things in the upper right, the electrons in the outer shell, are held more tightly, and things in the bottom left, the electrons in the outer shell, are held more loosely. And these are sort of the reasons why we see these periodic trends here. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.